Hey, pre-calc, we're going to start in with 9.8, and there's a lot of definitions, a lot of problems going on here, and it starts with the fundamental counting principle. Okay, so the fundamental counting principle is basically like, hey, you're trying to decide between, I don't know, lunch options. So with lunch, they say, hey, you can choose, I don't know, a hamburger, hot dog, or I don't know, just a sandwich like a grilled cheese or something. GC. And then from there, you get to choose different kinds of chips. So maybe they have regular and I don't know, barbecue. Regular, barbecue, regular, barbecue. And then from there, maybe you have a few soda options. Maybe there's 3 of them. Soda, diet, or water. Soda, diet, water. Soda, diet, water. So the fundamental counting principle is basically, instead of making a chart that breaks down, you can say, okay, well, I had 3 options for the first one. Then I had 2 options for the middle one. I forget what those were. Chips, that's what it was. And then we had 3 options for the third one. The fundamental counting principle says, hey, just multiply those numbers, those options together. And that's what this is in Word. So my made-up scenario I just came up with, it would be 6 times 3 or 18 is how you would do that. Okay, so there's also the permutations. So we call it a permutation because it is the NPR that we've been talking about so far. We use permutations when the order matters. So what that means is getting first is different than being selected second, which is different than being selected third, so on and so forth. So just so you know, n factorial is a form of a permutation. It's a permutation because every thing matters. But the reason why we have a certain kind of permutation is because maybe after you get third place, like maybe first gets a trophy, second gets a smaller trophy, and third gets, I don't know, a ribbon, and then fourth place and so on, they don't get anything. We would do a permutation for that one. Here's another. Oh, this is the definition. I don't know why I wrote that on there again. We've seen this before. You know how to do a permutation. I already talked about the order on this. And feel free to pause the video or read the notes more closely, because the next one that we have is what's called distinguishable permutations. So what distinguishable means is basically that you might have some repeats. I think I have an example of this one very early in the notes. But what we do is this formula, and it will make a lot more sense when I actually get to that problem. But distinguishable might mean repeats. So just be on the lookout for that one. And then we also have combinations, and we use this formula, which I think I asked you to prove this formula somewhere in the homework, which is pretty straightforward. I bet you can figure that out without any guidance. But we use a combination when the order does not matter. And you might be thinking, well, when would order not matter? Because so far, for our fundamental counting principle and permutations, I've talked about getting first place, second place, third place. Well, what if my go-to example is a field trip? Who cares if you're picked third to go on a field trip? What's the difference between being picked first or being picked third? You still get to go. So if the order does not matter, then we're going to use a combination. So there's little tricks along the way. Again, feel free to pause the video and explain and reread these notes. But this is exactly what I said. If the order matters, if the order is important, use a permutation. If the chosen elements is not important, so my go-to example of a field trip, it's a combination. Not important, combination. And then 2 or more separate categories, separate events, we're going to do the fundamental counting principle. So this first one is getting you to practice that. We are flipping a coin, a heads and tails coin, and a six-sided die. And you've seen my tree diagram actually already. And you don't have to have anything naming the diagram. You can just start with, okay, heads or tails. I'm only doing that one first because it was written first. You could also do this a little bit differently. And then a six-sided die, you can look at that. Okay, we have 1, 2, 3, 4, 5, 6 options there. And then after doing a tails, there's also 1, 2, 3, 4, 5, 6 options. So how many total options, if you count them up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's the number of outcomes we could come up with. And I've kind of ruined this. I've already given you the shortcut. The shortcut to figuring this out is there are 2 options for the coin. There were 6 options for the die. So 2 times 6 gives me 12. Whoa, that looked bad. 12 outcomes. So that's your shortcut for the fundamental counting principle. I'll shorten that. Fundamental counting principle. I don't think anybody shortens it to FCP, but there you go. So here's a problem where we have 10 runners entered into the 100-yard dash. How many different ways could the runners finish first, second, and third? So you could use the fundamental counting principle, but I want you to also understand the permutation. And so what the fundamental counting principle is, and I think I've talked about this in an earlier video, is you could just write out 3 places because you have 10 runners that could get first place. But then one of those runners has to get first. So how many options do you have for second place now? 9. And then how many options do you have for third place? 8. But the reason why this is a permutation is because the order matters. Getting first is different than getting second. And getting second is different than getting third. So we would set this up as 10, because there's 10 runners, permutation 3, because there's 3 positions, first, second, and third. And we could solve this by doing 10 factorial divided by 7 factorial, because you subtract the 2 numbers factorial. So why is that equal based off of math I've shown you how to do before? So you could rewrite this problem like this, and you get the same answer of 720. 9 times 8, 72, times 10 will give you that. So I could ask a question and ask you to set it up this way, to set it up this way, this way. That's kind of the downside to a multiple choice, is I could ask the same question and give you like 4 different options here. So as I move forward to the next one, and by the way, if you have any questions, write them down, bring them to class. We have 12 songs for Darla's workout playlist. She has to put, I guess to her, she puts her MP3 on a random, no repeat setting. So once you hear a song, you can't hear it again. So in how many different ways, how many different orders could Darla listen to all 12 songs? So you could do it this way. You could set it up as 12. So she had 12 songs to listen to the first one, but then if you can't repeat, then there's only 11 for the second. I'm already tired of writing this. I hope you see the pattern. If you don't see the pattern, please let me know. And we want to listen to all 12 songs, so we go all the way down to 12. So how is this as a permutation? It's 12p. You got to listen to all 12 songs. So this is the same thing as 12 factorial over 0 factorial. And as a reminder, 0 factorial is equal to 1. So this is the same thing as just 12 factorial. And I think they want the integer answer. Yeah, that's what that last thing is. So I'm going to cheat and go to my calculator and hit 12 factorial. Holy cow. I'll let you copy down the answer right there. 479 001 600. Holy cow. So 479 million different ways that she could listen to her MP3 player. Okay, I knew that it was pretty early in my notes that I would have this distinguishable permutations, and this is what I'm talking about. So they want to rewrite the word Mississippi in different ways. But here's the thing, we could write Mississippi this way, or we could swap some letters around. So what if I just swap these two? Well, if I swap those two, I get a different word. IMSS, yada, yada, yada. But here's the thing, is if I swap these two letters and I switch back to MI, so it's MISS, ISSIPPI, it's still the same word. So those are not distinguishable. So I hope that makes more sense when I started to talk about distinguishable permutations, that the order matters. I need to stay away from that phrase because it's not a permutation in that sense. But because we have repeats, by switching letters around, it's going to mess things up. Yeah. So if I go back to that formula, here it is. The n factorial is the total number of letters, but the n1 is the number of repeats. The n2 is the number of repeats, things like that. So I'm going to do this kind of a long way. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters, so 11 factorial. What I typically do is I just start with the first letter, which is M, and you see how M doesn't repeat anywhere. So I just write that there's one M, but you write as 1 factorial. So then I go to the next letter, which is I, and that repeats 1, 2, 3, 4 times. And then I look at the next letter, which is S, and that repeats 1, 2, 3, 4 times. And now the next letter is S. Well, we already counted S's. I's we already counted. S's and I's we already counted. We're left with 2 P's. I really hope I spelled Mississippi correctly. I'm notorious for misspelling words. I'm going to check that. All right, I'm pretty sure I spelled it right. Even if I didn't, let's just do the problem the way it's spelled. You can double check that you counted correctly, though, because the sum in the denominator needs to equal the numerator. So 4 plus 4 is 8, plus 2 is 10, plus 1 is 11. And that's why I even write down the non-repeats. Even though I know 1 factorial is 1, it helps me because, well, I like to write it out. So I would do this by hand. I know you can use a calculator. And I would stop at 4 factorial because I want to cancel out one of those 4 factorials. I'll cancel out the second one. And then 2 factorial is just 2. But the reason why sometimes I write it out is so I can see the 4 times 2 will cancel out with 8. And 3 times 2 can cancel out with 6. So in my calculator, instead of writing this out, I can just write 11 times 10 times 9 times 7 times 5. I hope I really wrote that correctly. Otherwise, you could double check 11 factorial over 4 factorial 4 factorial 2 factorial. And I think it still works even though I didn't put multiplication. Yep, I got the same answer there. So there's 34,650 different ways that you can rewrite Mississippi and get a different word. 34650. Distinguishable ways. Because if you just wanted to rearrange the letters, it would just be 11 factorial, but you might get repeats in there. That's why that's a big deal. So I'm at my time limit. I do know I have one more page of exercise 5 and 6. Oh, there's that proof I was going to do. I don't think the second video will be very long, but I'll see you there to get you ready for this homework.